In this video, we are going to focus on having a look at the reactivity of halogens. This is very different to the reactivity of group 1 elements. If you recall, going down the group for alkali metals, which are group 1, the reactivity increased. So the metals became more reactive as we went down the group. Whereas for the halogens, it's actually the opposite. So the reactivity decreases as we go down the group, and we will have a look at why, as you need to be able to explain that for your exams. So I'm just going to focus on fluorine and iodine just because they're on either end of our spectrum. Okay, so what is it that your halogens are trying to do when they react? Your halogens, as opposed to your alkali metals were losing the outer shell electron to become stable when they react, whereas your halogens are trying to gain an electron because they only have 7 electrons in the outer shell because they're in group 7, so unstable. Therefore, we need to gain an extra electron to become stable and become your halide ion. So fluorine is trying to gain this electron to become the fluoride ion, like so. So we've gained that extra electron. I'm going to draw it as a dot. We end up with a -1 charge. So this is what your fluoride is going to do or wanting to do, and same for your iodide as well. Okay, and the easier it is for your halogens to do this process, the more reactive it becomes. So let's have a look at it further, and let's have a look at a deeper dive as to why it is easier for fluorine to do this as opposed to iodine. So remember, as we go down the group, your atomic radius increases. I have not drawn the inner shells, but there will be, of course, inner shells as well. And your positive nucleus is trying to attract this electron close to it. Your positive nucleus is trying to attract this electron close to it. In both of these scenarios, there's going to be a stronger attraction in fluorine for this electron than iodine for this electron. Let's have a look at the reasons why. Well, first of all, the atomic radius is smaller in fluorine, therefore the distance for the positive nucleus and the outer incoming electron is going to be less. So it's going to be a lot more closer in proximity, therefore it's going to be attracted a lot faster and quicker. Whereas in iodine, the atomic radius becomes a lot larger, so the incoming electron is a lot further away from positive nucleus, therefore the attraction becomes a lot less. And the second thing that also matters in this case as well is the shielding. Well, what is shielding? Shielding is just your inner electron shells that I have not drawn. So remember, as we go down the group, we're adding more electrons in. Therefore, they're going to occupy more electron shells, correct? As we go down the group, we end up with more electron shells, and these sort of acts as a buffer for the attraction for the positive nucleus and the incoming electron. So because I've added more electron shells in iodine, therefore the attraction for the positive nucleus and the incoming electron becomes less. Therefore, for iodine, it is harder for it to gain this electron as opposed to it is in fluorine. That's why the reactivity of our halogens decreases as we go down the group, because it's harder for us to gain that incoming electron as we go down the group. In the next video, we will try to put this into exam wording so you know what to write when it comes to your exam.